Hello friends. In this video we'll look into the derivation of Young's Laplace equation of surface tension. In last class we studied about the surface tension, how it arises and all. In today's lecture we'll look into the derivation of Young's Laplace equation. We'll look into the derivation of Young's Laplace equation for liquid jet, for soap bubble, for liquid jet, for bubble submerged in liquid and for liquid droplet. We'll derive for liquid droplet and then we'll apply the same concept for these remaining three. Now let us consider this water drop. Here Pi is the pressure inside the water drop and P naught is the pressure outside. This P naught is due to air surrounding the water molecule. Now when we zoom in this part of the water molecule, we get such surface over here, and where where R1 is the radius of this R1 is the radius of curvature of this part, R2 is the radius of curvature of this part, and d theta 1 is the angle for this radius of curvature, and d theta 2 is the radius of curvature, and this one is the area. That is, when we look into this three-dimensional, this is how this cut part, what we considered, looks like. Here we know that force is sigma times of length. That is, here length is r1 d theta 1. That is, we know that L is equal to r theta. By that, we know that here length is r1 d theta 1, and here length is r2 d theta 2. So the force, that is the stretching force, that is the surface tension force, what it becomes is sigma times of r1 d theta 1, and over here the stretching force, that is surface tension force, becomes sigma times of r2 d theta 2. Now let us consider this part in this section and this part in this section. Here we know that for this part, if we consider this radius of curvature, what is the force pulling this? Is this one. That is, for this part, here the force is acting, the surface tension force, and here. So by the above diagram, by this diagram, we come to know that here force is nothing but sigma r2 d theta 2. The same goes to the other side here, sigma r2 d theta 2. And we know here the angle is d theta 1 by 2, and the same goes over here, d theta 1 by 2. So this one becomes sigma r2 d theta 2 into sine d theta 1 by 2. And the same goes over here. And for this part, that is for this part, what is the stretching force? That is for sideways, for this molecule is getting stretched sideways. By what force? That is sigma 1. Let me change the color. Here it is, sigma r1 d theta 1, and here it is also sigma r1 d theta 1, and the sine component of this force is sigma r1 d theta 1 into sine d theta 1 by 2. Here also same, sigma r1 d theta 1 times of sine d theta 1 by 2. Here this is r1 d theta 1, this is r2 d theta 2. Now let us do the force balancing of this. That is, what we are coming to know is here, that is Pi is the inside pressure, that is inside pressure of this molecule is Pi, and outside there is force due to air, and also the surface tension force is also acting. The surface tension force, that is, we need to take this normal force, this part, we need to consider this part. So that is the total force acting on this part we have considered of water drop. What is that? So let us do the force balancing of that. that is Pi. Force is nothing but pressure into, okay, I have already written here, that is force is pressure into area. So that is Pi into what is the area? This is nothing but the area, that is length into width, that is R1 into d theta 1 into R2 into d theta 2. That is Pi into R1 d theta 1 into R2 d theta 2. This is inside pressure, so it should be balanced by the outside pressure, outside force. That is P naught R1 d theta 1 into R2 d theta 2. This is not just the outside force. The outside force is also due to surface tension force. That is, look, there are how many forces? 1, 2, 3, 4. These both are same. That is, we can take this as twice of sigma R2 d theta 2 into sine d theta 1 by 2 plus twice of sigma, that is R1 d theta 1 into sine d theta by 2. Here it should be sine theta d theta 2 by 2. And here sine, this d theta is very small angle. Therefore, sine d theta 1 by 2 is approximately equal to d theta 1 by 2. The same goes for sine d theta 2 by 2. Therefore, if we now what this equation becomes is Pi R1 d theta 1 R2 d theta 2 is equal to P naught R1 d theta 1 R2 d theta 2 plus sigma times of R2 d theta 2 into d theta 1 plus sigma R1 d theta 1 into d theta 2. Now let us call this equation as equation 1. Therefore, by dividing, see, R1 d theta 1, R2 d theta 2, here everywhere in this whole equation is common. Therefore, we will divide by it. That is, divide by R1 R2 d theta 1 into d theta 2. Therefore, what we will get is Pi is equal to P naught plus sigma by R1 plus sigma by R2. Because there is no R1 term here, therefore here R1 comes here as denominator. There is no R2 term here, therefore R2 comes here as denominator. Therefore, now this equation becomes Pi minus P naught. Let us take this P naught that side is equal to, and let us take sigma as common here. We'll get 1 upon R1 plus 1 upon R2. This is equation 2, and this is what the derivation is. And we should remember that here we have considered water droplet. That is, there is only one interface. That is, here only air is only outside over here. Suppose if we consider as a bubble, air bubble, there is air inside here and air outside here. That is, there are two interfaces. So for two interface, we need to multiply here by 2. That is, for single interface, it is pi minus p naught is equal to sigma in the bracket 1 upon r1 plus 1 upon r2. For two interface, it becomes twice. Now, let us look at the formula. Like we have come to know for liquid droplet, that is what we had considered. What we got is pi minus p naught is equal to sigma in the bracket 1 upon r1 plus 1 upon r2. Suppose if you consider r1 is equal to r2, suppose if we consider r1 is equal to r2 is equal to r, this becomes implies pi minus p naught, and if we consider this in terms of diameter, this becomes pi minus p naught is equal to 4 sigma by d. For bubble, like I said just now, for bubble it is two interface. Air is here inside and air is here outside. That is, pi minus p naught becomes 2 sigma in the bracket 1 upon r1 plus 1 upon r2. And here, even if you consider for here also, r1 is equal to r2 is equal to r, then this becomes pi minus p naught is equal to 8 sigma by d. When you solve this, you will get this. And for liquid jet, here the catch is this is circular, that is, here there is r1, it is this one, but for line we know that radius is infinity, that is r2 is infinity. For line, radius of curvature will be infinite, that is r1 is equal to r and r2 is equal to infinity. So by applying above formula, that is pi minus p naught is equal to that is 1 upon, that is sigma in the bracket 1 upon r plus 1 upon infinity is 1 upon 0, that is this becomes 0, this becomes sigma by r, or if you want to write in the diameter form, this becomes 2 sigma by d. Now coming to this bubble submerged in liquid, look, this is bubble, air is over here inside, but there is air is not there outside, so this becomes again single interface. So many people get confused in this thing. This is single interface itself, that is pi minus p naught will become like, this is the same, this will become the case of the same thing, that is pi minus p naught is 4 sigma by d. Okay, in the next video we'll look into the problems regarding the Young's Laplace equation. Thank you.